Okay, this is all part of chapter 18 and 19, and I've narrowed down chapter 18 to the important parts about flow and displays. Otherwise, we're going to pick up that chapter when we get to vascular. So let's go over some of the Doppler display types and the system controls. First of all, it's important that you understand a little bit about flow. So the term monophasic means that you have flow on one side of the baseline. Typically, this is a term we use to describe abnormal arterial flow. So again, I just want you to be acquainted with the word monophasic, but generally this would be considered something we would call abnormal if we were to see something that looks like this, where it's just one little phase of systole and no diastole. Biphasic, most of your arteries are going to be a moderate resistant with two phases, and we refer to these two phases as a biphasic flow pattern. This would be our systolic phase, and this would be the diastolic phase. Systolic is the squeezing phase of the heart, and the diastolic is the resting phase. Our extremity vessels tend to have triphasic flow. Triphasic is flow that starts on one side of the baseline, it crosses then and reverses, and then returns to the original direction. So extremities like our upper arms and our lower legs, the arteries there would have a rapid acceleration, a sharp peak, rapid deceleration, a bit of reversal because the arterioles are pinched off or closed unless we're actually exercising. And then this little third component of forward flow comes from good compliant vessel walls. It's a snapback effect. So when a high pressure wave goes through an artery, it stretches out, the flow goes forward. If the arterioles are closed off, we're going to have a little bit of reversal, and then there's going to be some snapback of that artery that you see here, and that's the third component of a triphasic waveform. So there's two display types, and if you remember from the last lecture, the one on the left here that displays the information as an averaged value or velocity over time was created by a continuous wave system, and this is an analog display, right? So this is a continuous wave analog display, and on the right, this is a spectral display created by pulse wave Doppler. Okay, so these are the two types of Doppler, and we can tell what they are just by looking at the display. So the one on the right that's created by pulse wave uses FFT. The one on the left uses a zero crossing detector. Antegrade versus retrograde. These are terms that are important to remember. Antegrade flow means that it is flow going in the correct direction for a particular vessel. So before you can determine whether or not somebody has antegrade flow, you should know what direction the flow is supposed to be going by knowing your anatomy. Okay, and then retrograde flow is a term used to describe flow going in the wrong direction for a vessel. Now, this is completely different from positive and negative shifts. So let me go over a couple of things on this slide. First, I want to make sure you understand, I know we haven't gotten to the color packet yet, but that when you're looking at a color map and reading the information on a color map, the color on the top is the positive color assignment and the color on the bottom is the negative. So let's look at both of these scales. Both of these scales are set up so that blue is the positive shift and red is the negative. Usually when we turn on our system, it boots up the other way. Usually red's on the top and blue's on the bottom, but it absolutely does not matter as long as you understand how to read the color map. So this is what I want you to make sure you know. Now, before you can assess whether or not flow is normal, you need to know the direction of flow and the position of your transducer. If we're looking at the vertebral artery, and this is a common vessel we assess for flow direction, you need to know that if your notch is pointing up and you're holding your probe correctly, this should be the patient's head towards the left of the screen, and this would be the patient's feet on the right of the screen. And we're looking at a sagittal view. And in this picture, we have the vertebral artery along with the vertebral vein. And we always have a little area of shadowing because it courses through the cervical vertebrae. And there's going to be a bone in this section, which is going to attenuate the sound. So we usually get little pieces of the vessels. So if you knew your anatomy, you'd know this is the artery, okay? And again, this is the vein. And I'm just telling you that because you haven't studied your anatomy yet. So let's determine whether or not this person has antegrade or retrograde flow. And we want to do this by looking at the color box and the color map, and then looking at the direction in which we're sending in the sound beam, and then determine what direction is actually, which direction it's actually flowing. So I'm going to use a different color here. So I'm going to use the yellow. If this is our sound beam, and this is the direction in which the transducer is viewing the flow, and again, we know this by the color box and by the beam, because the color box is exactly the same tilt as the beam. We have our sample gate right here in the vessel, okay? So we're sending our beam in this direction, and we're receiving in this first vessel a negative shift. Now we know the only way the machine would record a negative shift is if the flow is going away from the transducer. So that would mean in this first vessel, the flow is going this way. The second vessel is filling in blue, which, if you look at your color map, is the positive color flow assignment. So that means this bottom vessel, the blue one, is going in this direction because the two arrows are going to hit, and that's a positive shift. So if we look at the artery and the vein, if it's an artery, the flow in the artery is supposed to go away from the heart towards the organ, in this case, the back of the brain. So if you look at the artery, it is going towards the head, okay? So the artery is flowing towards the head, so we would say that is antegrade flow in the artery. Antegrade means in the direction it's supposed to be going, completely different from positive or negative shift. A positive shift versus a negative shift, again, has to do with whether the frequency coming in is greater or less than the one sent in. Don't confuse these. Why am I emphasizing this? Because people confuse this all the time. Positive and negative has nothing to do with normal direction or abnormal direction. So in this first picture here, the vertebral does in fact have antegrade flow because it's flowing in the direction it's supposed to be. It also happens to be a negative shift, right? So if you look at this vessel right here, the first vessel, we are getting a negative shift because it's filling in the color red, which is exactly the way it's supposed to be going if it's going towards the head. Now looking at this second vessel, and this is the artery again. The vein isn't filling in very good, but the vein is down here. Okay, sometimes the vessels don't fill in very good if we don't have a good angle. So in this time we only have one vessel filling in, but we know the artery is on the top and the veins on the bottom here. So when we look at this and we look at our map assignment, positive is color-coded blue. Negative is color-coded red. Since the vessel is filling in blue, and this is the direction of the beam, that hasn't changed, and we're getting blue, that means that the sound source and the receiver are moving towards each other. So if this is the case, and this is the artery is supposed to be going towards the head, which is on the left of the screen, not towards the feet. So this person has retrograde flow. Okay, a couple of controls to make sure you're understanding how to use them and and what they do. The wall filter, by definition, is a filter, just as it says, and it's used to eliminate the very high amplitude, often very slow or low frequency Doppler shifts that usually come from vessel wall motion or cardiac valve motion. So we don't make this too complicated. When they say high intensity, when you're looking at a spectral display, that means that it's bright. See how shaded in this is and very, very bright? That's what they mean by intensity, high intensity. When they say low frequency, you can actually define this as low frequency or velocity because they both show up on the scale. On the y-axis. It depends on what we set it up for. So this y-axis right here is going to be either velocity or frequency. Most of the time it's velocity. So when they say it's used to eliminate high intensity, low frequency, or velocity shifts, they're talking about this right here. Little bright things, bright areas, meaning high amplitude. Low velocity, because if you bring that over to the scale of velocities, it's traveling at a very slow speed, usually due to wall motion or noise or something that's not part of the signal, usually. Okay, so this is what we're looking at. On the Doppler display, we usually refer to this little mark here of high amplitude, low velocity as clutter. So when the wall filter is set at 50 hertz, we're getting clutter on the display. To eliminate the clutter by increasing the wall filter, we are filtering out anything basically that's 75 hertz and below. So if that signal was below 75 hertz, it's going to be cleaned off of the display. Now the problem with setting a wall filter too high, like in this last scenario here, is not only is everything under 550 hertz and below being filtered out, but also the actual signal. We're missing a whole lot of the signal because it's supposed to look like this middle one. So the middle one is the best wall filter setting. It eliminates clutter, but it doesn't eliminate the signal. So sometimes you have to find just the right range to get just a clean signal that has no clutter and it doesn't erase any of the true signal. So on the registry, they give you pictures and they ask you, how can you fix this image? So if you were given the picture on the far right and they asked, what could you do to fix that? You would lower the wall filter. You want to take the wall filter down so you're filtering out less and you're letting more signal in and filtering less out. If they showed you the picture here on the left, how would you get rid of the clutter? You would increase the wall filter just a little bit, right? We don't want to increase it so much that we eliminate some of the signal. So you're going to get pictures where the controls are not in the proper range, and you have to adjust them until they are. Now the problem is you have to know this in theory, not so much with images. You can't just play like you can on your machine and touch the button until it looks the way you like it to look. They're going to ask you by giving you actual numbers. The wall filter was set at 50. Your image is showing clutter. What would be a new wall filter setting or a good wall filter setting? And you'd have to pick from your options. That's just one example. They can ask any kind of question they want. So make sure you're familiar with what the wall filter does and its uses. Again, to eliminate clutter, the best thing you can do is increase the wall filter. So here's the clutter that's showing up on the display. Let me put it in blue. It's all this like little noise around the baseline that we want to eliminate without eliminating any of the signal. So to get rid of clutter, we increase the wall filter. We want to filter that off of the display. I don't know what happened to them. We talked about instrumentation, and we mentioned reject before as one of the receiver functions, the last receiver function. We also know that there's an external control for reject. And this external control does the same thing. It filters out any low-level echoes from the grayscale display. So if you look at this picture here, there's a bunch of little echoes in here, and it should be nice and anechoic. We don't want those echoes in there. So the adjustments we can make is increasing the reject button or threshold or suppression. Those are the three different names that the manufacturers typically call reject. So by definition, it filters out low-level echoes. So hopefully it will clean up that image and sharpen it up when you increase that button. Range, gate, or sample volume. This allows the operator to select a specific depth at which to display the frequencies on the Doppler spectrum. Now, there's a gate that we use, or box when it's color, and a gate when it's Doppler. So here's our spectral display with our zero baseline here. We have a positive and a negative, right? So what they're referring to is this is what we call the gate, okay? And we call it a color box when we're using color, and that would be this. Okay, so the gate, we can be very selective with our gate. Some systems call it a sample volume, and when they call it a sample volume, it's because it looks more like a little circle and it's filled in. Now, when it says it allows the operator to change the sample volume and location, we can make this gate, and let me show you, the gate here is set like this. It's fairly small. We can send in a gate that's large and sample all of the red blood cells that travel through it, or we can be more selective and place it strategically where we want, in the middle of the vessel, along the edges of the vessel, so we can select exactly where we want our red blood cells to be recorded from. And again, this is what it would look like if we're recording our red blood cells within the gate. Velocity scale, which is linked to the PRF. This button allows the operator to change the scale of velocities or frequencies that can be displayed on the y-axis on the spectrum. And by adjusting the velocity scale, what you're doing is you're indirectly changing the PRF as well. Remember, they're linked together. Now, I know this is small and hard to see, but on the top here it says on the left-hand screen that this scale is set at 200. So it goes from 0 here to a maximum of 200. And again, you get to select the maximum value. Now the same vein, we're listening to the portal vein here. When we have a lower scale where the maximum velocity is only 50, you can visually see some of the differences, okay? Now, this is the same vessel, and the average speed of this vessel is traveling at about 30 centimeters per second. So to appreciate the detail of that flow, you'd want a lower PRF or velocity scale when listening to slower flow like this. A range of about 30, it goes up and down from 30, 40, 20, something like that, has a little undulating flow pattern. We want to see it where we can appreciate all the different velocities. Look at the problem with the scale on the left, the high velocity scale that's set at 200. It looks almost like just a little straight line. You could almost miss the flow and think that's just part of the baseline. The scale is set too high. And we know what happens when the scale is set too low, especially when listening to arteries. If the PRF is too low, we're going to get aliasing, where the peak is clipped off. So they're going to show you pictures where aliasing is happening, and they're going to ask you what you need to do to fix it. If there's aliasing, you want to increase the velocity scale or the PRF. But when you're listening to slow flow, if your scale's too high, you can't appreciate the details, and then you would want to lower your PRF or your velocity scale. So you want to set it just right for the speed of the flow. You don't want aliasing, and you don't want to miss anything. These are some parts of a waveform that you might want to get familiar with early on. They label this peak systolic velocity because this is the systolic phase here, and that's the peak velocity during systole. This is the diastolic phase, and EDV stands for end diastolic velocity. It's the velocity at the very end of the diastolic phase. The outside, the shaded part, they're calling here spectral intensity or spectral width. A lot of times we call that the envelope, and underneath the envelope is the window, the spectral window. We usually want this section clean if we're using a small gate on a vessel, but we'll discuss this a whole lot more when we get into vascular. I just wanted to introduce parts of the waveform so you kind of have an idea of what you're looking at. And this is a range of velocities over time. So this is the y-axis here, right? It can either be expressed in velocity or frequency. This is the x-axis. That's our time. And then the z-axis, which is our amplitude, the strength of the signal. See how bright it is during diastole? That means there's a lot more red blood cells traveling through, and therefore more are being recorded, and there's a higher amplitude. A couple more parts of a Doppler display here. They're showing you again, this is the peak systolic velocity, the end diastolic velocity, and the zero baseline. But when you look over on the left, this is showing you that this is the beam. This right here, they're calling the sample volume. If it were to look like this, they'd call it a gate. So sample volume and gate are the same thing, okay? And then the angle correct, let me clear this out, is this line right here. We set this at 60, and then we make sure it lines up with our vessel wall. That's how we know that we're accurately obtaining the correct velocities for physician interpretation. So if our charts are going to be set at a 60-degree angle, we want to make sure we're sampling at a 60-degree angle. So we line up, we set this up, beam and the guide, or the angle correct, at 60 degrees. And let me show you this a little bit better. Where's the 60? Okay, if this is the angle correct, and this is the beam, this is the 60-degree angle right here. And let me highlight that for you in yellow so you can see it's this angle of the flow to the beam. That's the 60-degree angle that they're referring to. So that you don't have to eyeball the angles and figure out what angle you're actually scanning at. That's what the angle correct cursor allows you to do. The angle correct allows you to position or set up your protractor so it says 60 degrees. And then if you line it up with the vessel wall right in the middle, okay, like that, then you do in fact have a 60-degree angle. And the information you provide will be accurate, but not if that guide isn't set at 60 and lined up in the center of the vessel. Now, I've seen some people do this. They'll scan where their beam's coming in, and their guide's like this. And it may say 60, but if they're not lined up with the wall, see how that's not parallel, then you don't, in fact, have a 60-degree angle. Now, that isn't a 60 set, but that's just an example. Okay, so that's a couple of the controls that you're going to practice playing with. And in fact, if you come in, I'll be on campus Tuesday and Thursday. You're welcome to come in, and we can go over some of the controls at that time.